Welcome! In this session, we'll be diving into problem number 1204, titled Last Person to Fit in the Elevator. This engaging problem will challenge your algorithm design skills as we explore different approaches to solve it. Let's get started. In this problem, we are tasked with simulating the behavior of an elevator with a maximum weight capacity, which is defined by the variable max weight. You are also given a list called weights, where each element represents the weight of a person waiting in line to enter the elevator. People will attempt to enter the elevator one by one in the order they appear in the list. The key condition here is that the elevator will stop accepting new passengers as soon as the weight of the next person would cause the total to exceed max weight. The goal is to determine the zero-based index of the last person who successfully enters the elevator before it becomes full. If no one is able to enter the elevator, due to their individual weights exceeding the capacity, we should return -1 as the result. Now, let's examine how the input and output are structured in this problem. The input consists of two main components. First, we have weights, which is a list of integers representing the weight of each person in the queue. The size of this list is denoted as n, and it tells us how many people are in line. Second, we have max weight, which is a single integer specifying the maximum weight capacity of the elevator. The output for this problem is a single integer. This integer represents the zero-based index of the last person who successfully enters the elevator. For example, if the output is 1, it means the second person in the queue was the last one to get in before the elevator reached its weight limit. If no one is able to enter the elevator at all, the output should be -1. To solidify this understanding, let's look at some example scenarios. Consider the first example. Here, the weights list is 60, 80, 40, 50, and the max weight of the elevator is 100. The first person, weighing 60, enters, and the total weight becomes 60. The second person, weighing 80, would cause the total to become 140, which exceeds the capacity. Therefore, they cannot enter. This means the last person to successfully enter was the first one, at index 1. In the second example, the weights list is 40, 50, 70, 30, and the max weight is 150. The first person enters, bringing the total to 40. The second person enters, bringing the total to 90. When the third person tries to enter, their weight of 70 causes the total to reach 160, which exceeds the capacity. Thus, the last successful entry was the second person, at index 2. Let's explore another example to understand edge cases. In the third example, the weights list is 120, 130, 140, and the max weight is 100. Here, the very first person in the queue weighs 120, which already exceeds the elevator's maximum capacity. Hence, no one is able to enter the elevator. In this case, the output is -1, as there are no successful entries. This example highlights a key edge case, where the weights of all individuals in the queue exceed the elevator's capacity. Now, let's address some additional constraints and edge cases to ensure our understanding is complete. There are several constraints and edge cases to consider for this problem. First, the length of the weights list, denoted by n, ranges between 1 and 10,000. This ensures that the input will always have at least one person, and we must handle large queues efficiently. Each person's weight, represented by weights, I, can be as large as 100,000, while the maximum capacity of the elevator, max weight, can go up to 1 billion. This means the solution must account for very large numbers and perform computations efficiently. Edge cases include scenarios where all individuals are too heavy to enter, where only one person fits exactly within the capacity, and cases where the total weight perfectly matches the elevator's capacity after adding a person. Finally, while an empty weights list is not valid under the constraints, the solution must be robust enough to handle the upper bounds of input size without any performance issues. When considering the brute force approach, the intuition is straightforward. We iterate through the list of weights and maintain a cumulative sum as we process each person in the queue. The goal is to track the weight being added to the elevator until we reach the maximum capacity. As soon as adding another person would exceed the elevator's maximum weight, we stop and return the index of the last person who successfully fit. The algorithm to achieve this is simple: initialize the current weight to 0 and a variable to track the last valid person is -1. Then, as we iterate through the weights, we add the current person's weight to the cumulative total. If this total surpasses the maximum allowed weight, we exit the loop. Otherwise, we update the last person to the current index. Finally, we return the index of the last valid person. Although this approach is correct and ensures we meet the problem's requirements, it may not be the most efficient for larger input sizes. The time complexity of the brute force approach is O(n), where n is the number of people in the queue, because we process each weight exactly once. The space complexity is O(1), as no additional data structures are used, everything operates in place. Now, to optimize this process, we can make use of the principle of early termination. By leveraging the prefix sum of weights, we can stop processing as soon as the sum exceeds the elevator's maximum capacity. This optimized approach simplifies the brute force logic and emphasizes efficiency by avoiding unnecessary calculations after exceeding the weight limit. The algorithm for this optimized version remains similar: maintain a running sum for the cumulative weight, and as soon as it exceeds the maximum allowed weight, return the index of the last valid person. The time complexity is still O(n), as we process each weight once, and the space complexity remains O(1). This optimization is subtle but aligns better with the problem's constraints by emphasizing early exit. The chosen strategy for solving this problem is rooted in some key observations. First, the problem is inherently sequential, meaning we must process the queue in order to determine the last person who can fit into the elevator. This eliminates the need for any complex data structures or algorithms. Another important realization is that the brute force and optimized approaches are nearly identical in terms of time and space complexity, both operating in O(n) time and O(1) space. However, the optimized approach stands out because it prioritizes stopping as soon as the weight limit is exceeded, which highlights a more efficient way of thinking about the problem. By framing the solution around early termination, we reinforce the importance of minimizing unnecessary calculations. Sorting or binary search, while useful in other scenarios, are unnecessary here because the weights are already processed sequentially, and no pre-processing is required. The simplicity of the optimized approach, combined with its alignment to the problem's constraints, makes it the most logical choice. In conclusion, the optimized approach is the best choice for solving this problem due to its simplicity, efficiency, and alignment with the problem's constraints. By processing each weight sequentially and stopping as soon as the capacity is exceeded, we ensure the solution is both time efficient and space efficient, operating in O(n) time and O(1) space. This approach avoids unnecessary complexity while directly addressing the requirements of the problem. By focusing on early termination and leveraging the sequential nature of the queue, we achieve the desired outcome with minimal overhead, making this the most practical and effective strategy. The problem at hand requires us to determine how many people can board an elevator without exceeding its maximum weight capacity. Given a list of weights representing the individuals in line and a maximum allowable weight, our task is to identify the index of the last person who can safely board before the weight limit is breached. To do this, we start by initializing a variable called current weight to 0, which will keep track of the cumulative weight of the individuals as they board. Using a loop index I, we traverse through the list of weights. For each person, we add their weight to current weight and immediately check if this total exceeds the elevator's maximum capacity. If it does, we stop processing further and return the index of the last person who fit successfully, which is 1(1). If the weight does not exceed the limit, we proceed to evaluate the next person in the list. Now, it's important to address edge cases. For instance, if the list of weights is empty, there's no one to board the elevator, so we simply return -1. Similarly, if all the people in the list fit within the elevator's capacity, we return the index of the last person in the list, as everyone is accommodated. The final output of the algorithm is the index of the last valid person who fit in the elevator. By maintaining a running total of the weights through current weight, we avoid recalculating the cumulative weight repeatedly, which makes the algorithm efficient. Furthermore, terminating the loop as soon as the capacity is breached ensures that we save on unnecessary computations. The algorithm is robust due to these considerations, including checks for empty lists and handling scenarios with very large weights. The data structures involved are minimal, as the input list is accessed sequentially, and scalar variables track the weight in index. This simplicity ensures the algorithm remains efficient and easy to implement. Analyzing the complexity, the time complexity of this algorithm is O(n), where n is the number of people represented by the length of the weights list. This is because we iterate through the list just once, performing constant time operations for each person. The space complexity is O(1), as the algorithm only uses a few scalar variables like current weight and I, without any additional data structures. Let's walk through an example to clarify. Suppose the input weights are 50, 75, 60, 90, and the maximum weight capacity is 200. Initially, current weight is set to 0. Adding the first person's weight, 50, results in current weight equals 50, which is valid. Adding the second person's weight, 75, gives current weight equals 125, still valid. Adding the third person's weight, 60, results in current weight equals 185, which remains under the limit. However, adding the fourth person's weight, 90, increases the total to current weight equals 275, exceeding the maximum capacity. At this point, the algorithm stops and returns I1, which is 2. In edge cases, such as an empty list, the result is -1 since no one can board. If all people fit, like 50, 75, 60, with a capacity of 300, the output is the last index, 2. If the first person alone is too heavy, such as 400, with a capacity of 200, the result is -1 as no one can board. These scenarios highlight the algorithm's flexibility and correctness. The algorithm is further optimized by exiting the loop early as soon as the weight exceeds the limit, ensuring no unnecessary computations are performed. The use of a cumulative sum, tracked through current weight, eliminates the need for redundant sum calculations, enhancing efficiency. Here's a pseudocode representation of the algorithm. Start by initializing current weight to 0. Loop through the weights using an index I. For each weight, add it to current weight. If the cumulative sum exceeds the maximum capacity, immediately return I1. If the loop completes without exceeding the capacity, return the last index of the list, or -1 if the list is empty. This approach works because it efficiently processes each weight exactly once, leveraging the sequential nature of the input list. The algorithm's simplicity ensures correctness, while the early exit and cumulative sum make it both time and space efficient. By focusing on these principles, we achieve an optimal solution to the problem while maintaining clarity and robustness in implementation. This Python implementation solves the problem of identifying the last person who can fit into the elevator without exceeding the maximum weight capacity. The class solution includes a method lastPersonToFit that takes a list of people's weights and the elevator's maximum weight capacity as inputs. We initialize current weight to 0, which tracks the cumulative weight of people already in the elevator. Then, we iterate through the list of weights using a for loop. For each person, we check if adding their weight would exceed the maximum capacity. If it does, we return the index of the previous person, i.e., I1, as the last person who can fit. Otherwise, we add their weight to current weight and continue. If the loop completes without exceeding the weight limit, it means all people can fit, so we return len, weights, 1, the index of the last person in the list. This solution is efficient with O(n) time complexity, where n is the number of people in the weights list. This is the Java implementation of LeetCode problem number 1204, last person to fit in the elevator. The logic mirrors the Python solution. The method iterates through the weights array and calculates the cumulative weight. If adding the next person's weight exceeds the elevator's maximum capacity, the method returns the index of the last person who could fit. Key differences in Java include explicit type declarations and the use of arrays instead of Python lists. To solve this problem, we start by initializing current weight to 0. The goal is to iterate through the weights array to see how many people can fit in the elevator before the weight exceeds the max weight. In this example, the input weights are 60, 80, 40, 30, and the maximum capacity is 150. For the first person, weights, 0, is 60. Adding this to current weight gives 60, which is less than or equal to 150, so we include this person in the elevator. The current weight is now updated to 60. Moving to the second person, weights, 1, is 80. Adding this to current weight gives 140, which is still within the limit. We update current weight to 140. For the third person, weights, 2, is 40. Adding this would make the total weight 180, which exceeds the maximum capacity. At this point, we stop and return the index of the last person who successfully entered the elevator, which is 1. The output for the first example is 1, meaning the second person, at index 1, was the last to fit before the capacity was exceeded. Now, let's analyze another example. The input weights are 50, 70, 20, 10, with a max weight of 100. Again, we initialize current weight to 0. For the first person, weights, 0, is 50. Adding this to current weight results in 50, which is within the limit, so we include this person and update current weight to 50. For the second person, weights, 1, is 70. Adding this to current weight results in 120, which exceeds the maximum allowed weight. Therefore, we stop here and return the index of the last person who successfully entered, which is 0. The output for the second example is 0. This means only the first person, at index 0, was able to enter the elevator before the weight exceeded the limit. Now, consider a third example with weights, 40, 30, 20, 10, and a max weight of 150. We start by initializing current weight to 0. The first person, weights, 0, has a weight of 40. Adding this to current weight results in 40, which is within the limit, so we include this person and update current weight to 40. For the second person, weights, 1, is 30. Adding this gives a total of 70, which is still within the limit. We include this person as well and update current weight to 70. For the third person, weights, 2, is 20. Adding this to current weight results in 90, which is within the limit, so we include this person and update current weight to 90. The fourth person, weights, 3, has a weight of 10. Adding this results in a total of 100, which is still within the maximum capacity. We include this person and update current weight to 100. At this point, all individuals in the weights array have been processed. Since no one exceeded the capacity, we return the index of the last person, which is the last index of the array, 3. The output for this example is 3, meaning all 4 individuals were able to enter the elevator without exceeding the maximum weight. The time complexity of the last person to fit method is O(n), where n represents the number of elements in the weights list. Let's break this down step by step. First, the for loop iterates through the entire weights list, meaning it can run up to n times in the worst case. During each iteration, 3 operations are performed. The addition operation, current weight plus weights, I, computes the potential new total weight, and this is an O(1) operation. Then, the comparison operation, current weight plus weights, I, max weight, checks if the total exceeds the allowed maximum weight, which is also O(1). Finally, the update operation, current weight plus equals weights, I, adjusts the cumulative weight, and this too is O(1). Since each of these operations takes constant time and the loop runs up to n times, the overall time complexity is O(n). Now, let's examine the best, average, and worst cases for time complexity. In the best case, the loop exits early. This could happen, for example, if the very first person exceeds the weight limit. In such a scenario, the method completes in O(1) time. In the average case, the loop processes about half of the list, which results in O(n) operations. Finally, in the worst case, all n elements are processed, leading to O(n) time. Shifting to space complexity, the method is highly efficient with an O(1) space complexity. This is because it uses a constant amount of memory regardless of the input size. The input list weights is provided as an argument, so it doesn't count toward additional space. The method also uses only 2 auxiliary variables, current weight, which tracks the cumulative weight, and I, the loop index variable. Both of these are scalar values, requiring only O(1) space. Since no other data structures are used, the space complexity remains constant. Let's compare this optimized solution with a brute force approach. A naive method might involve generating all possible subsets of the weights list to find the maximum weight that doesn't exceed max weight. This would require constructing 2 to the power of n subsets, resulting in a time complexity of O(2 to the power of n. Additionally, the auxiliary space needed to store these subsets would also be O(2 to the power of n, making this approach computationally expensive and memory intensive. On the other hand, the optimized approach directly iterates through the list while maintaining a running total, achieving a linear time complexity of O(n), and constant space complexity of O1. Mathematically, the time complexity is derived as follows: the loop runs at most n times, with each iteration performing constant time operations like addition, comparison, and assignment. Multiplying these, we get O(n) asterisk O1, which simplifies to O(n). For space, since the method uses only fixed-size variables, the complexity remains O1, regardless of the size of the input. One of the most common mistakes when solving problems like this is neglecting edge cases. For instance, what happens if the input is empty or contains just a single element? Overlooking these situations can lead to runtime errors like an indexer or produce incorrect results. Another frequent issue is not optimizing for time complexity. Let's say you're using nested loops in a scenario where a more efficient O(n) solution is possible. This might work for small datasets, but when the input size grows significantly, such as n greater than 10,000, your solution may exceed time limits. Misinterpreting the constraints or requirements is another tricky area. For example, assuming the weights are already sorted when the problem doesn't guarantee it can lead to invalid solutions based on incorrect assumptions. Additionally, incorrect variable initialization, such as setting a cumulative sum to the wrong starting value, can create logical errors, especially in approaches like prefix sums or sliding windows. These mistakes highlight the importance of a careful, methodical approach to problem solving. Overcomplicating your implementation is another pitfall to avoid. For example, adding unnecessary condition checks inside loops doesn't just increase the risk of bugs, it also makes your code harder to debug and maintain. Now, when it comes to interviews, there are some key practices to keep in mind. It's essential to understand the problem thoroughly. Take a moment to ask clarifying questions to ensure you're aware of all edge cases and constraints. Identifying patterns can also be a game changer. Techniques like prefix sums, sliding windows, or binary search often help reduce computational overhead. Remember to communicate your thought process clearly. Explain why you're choosing a specific approach and discuss its trade-offs. Testing edge cases is another critical step. Small and boundary test cases can help verify the correctness of your solution. Finally, if time allows, consider comparing multiple approaches. Discussing alternatives and explaining why you chose the optimal one demonstrates a deeper understanding of the problem. Understanding related problems can help you recognize patterns and apply techniques effectively. For example, LeetCode problem 1, 2 sum, involves finding pairs of numbers that add up to a target value. This often uses hash maps or two-pointer techniques. LeetCode 560, subarray sum equals k, requires a similar prefix sum technique, focusing on subarray sums that match a given target. Another interesting problem is LeetCode 42, trapping rainwater, which combines sliding window and prefix sum techniques to calculate trapped water efficiently. Lastly, LeetCode 977, squares of a sorted array, uses a two-pointer approach to handle sorted inputs in an efficient way. These problems illustrate the versatility of these methods and how they can be adapted to different scenarios. When considering alternative approaches, it's important to weigh their pros and cons. A brute force approach is often the most intuitive. It involves iterating through all possible pairs or subarrays. While it's easy to implement and understand, it's usually inefficient, with a time complexity of O(n) squared, or worse. On the other hand, optimized techniques like sliding window or prefix sums reduce redundant computations, achieving much faster runtimes, such as O(n). However, they may require additional memory, such as storing prefix sums. For sorted inputs, binary search is a powerful tool. It allows you to locate values efficiently with a time complexity of O log n, but it's only applicable if the input is sorted or can be sorted without significant overhead. Finally, hash maps are excellent for constant time lookups. They enable quick access to intermediate results, but they can require extra memory and need careful handling of edge cases, like hash collisions. Each approach has its trade-offs, so the choice depends on the problem's constraints and requirements. Great job! To wrap up, we reviewed the problem, summarized the key approach, and highlighted important takeaways. Keep practicing and exploring optimized solutions. Thanks for watching. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!